Hello, everybody. My name is Emanuele Rossi, and I'm a PhD student at the Faculty of Civil Engineering at TU Delft. And today I'm going to talk about the applicability of a precursor for bacteria-based self-healing concrete derived from waste streams. But before diving into the contents of this presentation, let me first thank the co-authors of this study, the PhD student Chris Vermeer and his supervisor Robert Klerebedzen from the Faculty of Applied Sciences here at TU Delft, and my two supervisors, Dr. Ozan Choporoglu and Dr. Henk Jonkers. So as the title suggests, today we're going to talk about self-healing concrete. And why is self-healing of concrete important? Because we know that concrete cracks because of its brittle nature and because of its weakness in tension. That is why we put reinforcement inside. The occurrence of cracks allow harmful agents from the outside environment to penetrate into the material, such as chlorides and CO2, that can influence negatively the service life of our infrastructures. But luckily, there are cracks that are not that dangerous for the service life of our infrastructures, because concrete has this autogeneous capacity to self-heal cracks physically, chemically, or mechanically. For example, through continuous hydration of unhydrated cement particles and through carbonation of the matrix and precipitation of calcium carbonates that can fill up cracks. The thing is that during the last 10 to 15 to 20 years of research, we, let's say the scientific community determined the maximum healable crack width that concrete is able to self-heal, that is around, in general, 100 to 150 micrometers, of course, depending on many interrelated parameters related to the mixture. Therefore, since actually self-healing of concrete might theoretically improve a lot the service life of our infrastructures, a lot of research has been spent during the last years to try to improve this self-healing capacity of concrete through many different technologies, such as including fibers in the matrix, so to limit the crack width to a healable crack width by the concrete, such as through encapsulating many types of different heating agents that can release a certain heating agent indeed as soon as the cracks occur, and then they can fill up the crack. And also such as through embedding in the matrix bacteria-based self-heating agents. So by including bacterial spores and certain nutrients and certain substrates in many different encapsulating technique that can indeed, these bacteria metabolize these substrates and then, let's say, cause precipitation of crystals that can fill up the crack. And this is the major group that we're going to talk about today. If we dive a little bit more into the, let's say, what has been done related to bacteria-based self-healing concrete, these two tables are a small literature review related tables that can that show certain heating agent types that have been proposed in the literature that you can see on the left, and you see that many different technologies have been used, such as calcium lactate derivatives, such as sodium alginate capsules and so on. But most of these actually didn't really consider the sustainability aspect related to the production process of these heating agents. And also on the right, we can see that most of the heating agents that have been proposed in the literature have been checked, or let's say applied in Portland cement based mixtures. And what we're going to do today is try to evaluate the applicability of a precursor that is alkanoids based, that is actually let's say made of wastes that are processed beforehand, so is theoretically more environmentally friendly than other techniques that have been proposed in the literature, and that is well, let's say that this part is going to be presented today. And this substrate is also potentially applicable or compatible with low alkaline cementitious materials, and this is part of ongoing studies that is not going to be presented today, but still just for as a potential further application and benefit of this heating agent. We know that what we do with our heating agent that is indeed alkanoid based is basically that we get biomasses from water plants, such as those that you see on the left side of the screen, and then out of these, through certain bioreactors at the Faculty of Applied Sciences, we get this bioplastic that looks like the powder that you see in the second picture from the left, and then we merge this bioplastic with nutrients for the bacteria and bacteria spores, and through a certain production process of the heating agents, then we get to the final heating agents that is powder-like, generally between 0.5 and 1 millimeter in dimension. And then we embed this heating agent into the matrix while we mix our specimens. And well, in order to evaluate the applicability of these heating agents, a former PhD of our department at TU Delft, R1 Emanuele Rossi A, proposed 3 factors let's say, performance that needs to be evaluated when indeed investigating the applicability of a certain heating agent in terms of indeed its self-heating capacity. And these are the occurrence of mineral formation thanks to the heating agents that is included, the regain of water tightness, so the crack sealing capacity of the material, and also the evidence of bacterial activity. So according to this, actually, we conducted a sort of experimental plan for Portland cement mixtures that aim to evaluate indeed the self-heating capacity and mineral formation of this system, the evidence of bacterial activity in the mortar, and also a little bit of influence on some fundamental functional properties of the material. And that is indeed the point that we're going to start with. So what we did for all these experiments that we conducted, we did 3 series, a control series that is made of plain ordinary Portland cement mortar with a water cement ratio of 0.5. Positive reference, let's put it this way, that embedded 2.6% by mass of cement of PLA or calcium lactate derivatives heating agents. That is the one that Hank, my supervisor, and also many other PhDs investigated during the last 10 to 15 years. And also we did another series of specimens with the ordinary Portland cement mortar, but including the same percentage of heating agent as the one of PLA, but with alkanoid-based heating agent. That is the one that we produce, and that is named as AKD. And as we can see in the bottom of the slide, we see that the hydration curve gets a little bit, let's say that the hydration curve of the cement paste, including AKD heating agent, is a little bit lower than the one of plain mortar, but that doesn't really have a negative influence on some functional properties, such as indeed the compression strength, as you can see on the right, since actually it's just a little bit lower at the very first days than the one of than the compression strength of the plain mortar, but at the end at 28 days it's even a little bit higher. So that is already pretty positive, because we checked or we can say that doesn't really have a negative influence, the heating agents that we include, on let's say some of them, some very important functional properties of the mortar. Then if we dive a little bit more into the self-heating capacity of it, what we did was cracking samples, making samples first, and then we cracked them at either 28 days or 6 months, as you can see on the left. And we calculated the self-heating capacity of a certain mixture as the ratio between the water flow that was able to pass through the sample just after cracking, and also the one that could get through the sample after self-heating. And in this case, self-heating, the self-heating incubation happened for 56 days in a high humidity chamber at a relative humidity higher than 95%. And what we can see on the graph on the left, we see that the self-heating capacity for the samples that were cracked at 28 days of the control, it has to be mentioned also that the cracks were around 500 micrometers in width. For the control series, so those with the plain mortar, the self-heating capacity was around 60%, while actually for both PLA and AKD, the self-heating capacity of these got quite higher at around 90% for those cracked at 28 days. Let's say the bigger influence is visible for the samples that were cracked at 6 months of age, since actually continuous hydration of the plain mortar, or the mortar in general, gets reduced with time. And then indeed we can see that the control series had an average self-heating capacity of around 10 to 15%, while actually the one of the PLA was around 40%, and we got a 4 times higher compared to the one of plain mortar self-heating capacity for AKD at 6 months. So we can indeed see how positive is the influence for cracks that are actually relatively big of our heating agents included in the matrix. And also that is also further confirmed from the pictures on the right, where you can see the first row related to the control series, where cracked at 28 days there is quite a bit of precipitates that cannot, however, fill up the crack completely, while actually for those cracked at 6 months the crack is more or less the same, so there is not enough precipitation to seal the crack for the control series, while for both PLA and PHPV or AKD, we see that the cracks get completely self-filled. What we also did was evaluating the mineral formation and bacterial activity through SEM analysis. So we made sections for that were perpendicular to the crack, and you can see some pictures about it on the left side of the screen. And you see that in the first row you have control specimens. Well, the sections related to the control series, and you see that actually the amount of precipitate is very limited. This is indicated by the white arrows. While actually for both PLA, which is the one in the middle, and AKD, that is the one at the bottom, you see that precipitates growing at the size of the crack are way more than those that we can see in the crack related to the plain mortar. So that is also confirming the ability, or let's say the compatibility of our heating agents with self-healing mortar. And also on the right, we see indeed calcium carbonate crystals that have bacterial imprints that are representative indeed, according to the literature, for bacterial activity in our matrix. Furthermore, we checked, we evaluated some, well, briefly, some transport properties of sound samples, so not of cracked samples, according to, so the chloride diffusion coefficient, according to the NT build, the 443 and the 492, and for the same mixtures. And we saw that the values for the control series were always very higher than those of the PLA and the AKD, as you can see in the table at the bottom. And that was why we didn't conduct MIP yet on these samples, but we observed precipitation of a thin layer of calcium carbonates at the surface of the sample that might be indeed responsible for the higher, let's say, the improved transport properties of our material. So we basically evaluated quite a few qualities or characteristics of our material that could indeed confirm the applicability of our heating agents with self-healing ordinary Portland mortar. What is also very important is that we know that indeed, in general, for certain applications, especially for infrastructures that are exposed to pretty aggressive environments, such as with a high content of chlorides, it's common, especially here in the Netherlands, to use slag cements, especially with high content of slag, such as SEM3P. And that is indeed in a country like the Netherlands that has more than 450 kilometers of coastline, the market share of slag cement is over 60%. However, a few heating agents that have been proposed in the literature are not really compatible with low alkaline cements. And especially if I consider the one that we took as a positive reference for our series, the calcium lactate derivatives, it needs high alkalinity to get metabolized by the bacteria. While, for example, in our case, the alkaline-based heating agent does not need alkalinity to get metabolized, and therefore is theoretically compatible with low alkalinity mixtures. And that is actually different from most of the proposed solutions. And the compatibility with our heating agent, alkaline based, and indeed the self-heating capacity of low alkaline cementitious materials is under development and under investigation in ongoing studies. And I hope that eventually in the coming future, I will be able to present some positive results. So if we want to conclude, from the present study, what we can say is that the application of 2.6% by mass of cement of alkaline-based heating agents, that is around indeed 10 kilograms per cubic meter of mixture, did not negatively influence the major functional properties of Portland cement mortar. That the applicability of alkaline-based heating agent has been demonstrated through the three factors that have been proposed earlier to evaluate indeed the applicability of a certain self-healing technology, such as through indeed mineral formation, regain of water tightness, and evidence of bacterial activity. That the self-healing capacity of alkaline-based mortar was equal to more than 90% to 65% for specimens cracked at 28 days and 6 months of age, and that it was higher not only of plain mortar specimens, but also on the positive reference specimens, and that the transport properties of mortar get significantly improved by the addition of AKD, thanks to a carbonate layer forming at the specimen surface. And also, as a potential for the application of this and for the benefit of this application, the theoretical compatibility with low alkaline mixture makes alkaline-based heating agent potentially of high market and scientific value. So that was it for my presentation. I thank you very much for your attention. And of course, if you're interested, just do not hesitate to send me an email, and I would be glad to answer your questions.